What's up, my chemistry students? Mrs. Thompson here, and today we're going to continue on looking at galvanic cells. Now we're going to calculate cell potential. So we should have already gone through figuring out which one's the anode, which one's the cathode, making the cell line notation, and even predicting the way that the electrons flow and the way that the ions flow. In order to calculate cell potential, we need standard reduction potentials. So you need a chart that looks just like this one. And in this chart, it shows you, in terms of reduction, different elements being reduced. And the Ecell. Notice it has this little degree sign, that's like a knot is what we call it. That's to show that these are happening at standard conditions. Standard conditions are 1 molar solutions, 25 degrees Celsius, and if it's a gas, it's at 1 atmosphere. This standard reduction potential, what they are, is a tendency of a substance to be able to gain electrons. Reduction. So the higher its potential here, its voltage, the better it is at gaining electrons and stealing those electrons from something else. It's a better oxidizing agent. It's measured in volts. The more positive the value of E, the more likely it is to be reduced. Cell potential is a measure of the potential difference between the two half reactions, or two half cells within the electrochemical cell. And so those values are here. So we'd find the difference between them. The greater the difference is between their values, the more electrons are going to be transferred. In order for a galvanic cell to be spontaneous, that means it would happen on its own. We wouldn't have to add any electricity. It produces electricity. That E cell has to be positive. And so every time we make one of these galvanic cells, we're going to set it up so that the E cell is positive. All right, so here's how you're going to do that. Here are the steps. Find both half reactions on that table, the standard reduction potential table. Identify the reduction half reaction. So we're going to figure out which one of those would be the reduction one, which one stays as is, and that would be the one that has the most positive value for that reduction potential. Then we'll find which one's going to be oxidation. The one that's going to be oxidation, we're going to flip that reaction and change the sign of E. Then, in order to make sure that all of the electrons lost are equal to all of the electrons gained, we are going to multiply the half reactions to make the electrons equal. We never multiply the value of E. So it's kind of like Hess's law in a way. The only difference here is we're not multiplying by the value of E. All right, so we're going to cancel the electrons and then add the two half reactions at the end. Okay, here's our first example. We're going to calculate the E cell and write the overall reaction for the reaction between zinc and silver. So we need our standard reduction potential table that looks like this. So get that one out. All right. So I have already taken care of that. I've looked those up. Here are their values and how many electrons they need. Okay. So second step is to figure out which one of these is going to be reduction. That's the one that is the most positive number. So this one is reduction. The other one is oxidation. All right. Next, to the one that is oxidation, we need to flip it. So we're going to multiply by a -1 so that it'll flip. Okay. There's something else I can take care of too at the same time, and that is the number of electrons. Notice that in this one I have 1 electron, and in this one I have 2. We want to make these two equal in terms of the numbers of electrons. So I'm going to multiply this whole thing by 2. All right, so let's rewrite both of those. Notice as I multiplied by 2, I did not multiply the value of E. So just leave the volts the same. All right, for zinc, what I did was I flipped it. So I turned it from a reduction potential into oxidation so that you see the electrons on the right side of the equation. And this went from being negative to being positive. All right, so then we are going to cancel the electrons and then write the overall reaction by writing what's left. So everything that's on the left side of the arrow, the silver plus 2 silver plus ions and 1 zinc solid. And then on the right side of the arrow is this and this. And then we just add the two E's together and we get Ecell, 1.56 volts. So if I take these two solutions and I put them together, or two half cells and put them together, I can get 1.56 volts from this solution, or from this reaction. All right, we'll try one more, and you might have to add this to your paper. Calculate the Ecell and write the overall reaction for the reaction between gold 3 and silver. Gold 3 is written here because there is another oxidation state for gold, that's gold 1. And so you're going to look up the one that's gold 3 or gold 3 plus. Remember, the Roman numerals mean the charge on the transition metal. All right, so here we go. Here's the value for gold 3. That's in terms of reduction. This one is also in terms of reduction. That's the zinc. All right, I have to decide which one is going to be oxidation and which one's reduction. Well, reduction is going to be the one that is the most positive, that one. This one's going to be oxidation. All right, so then I also need to decide what am I going to multiply these by in order to make an overall equation. And so what I should notice is the number of electrons are different. This is 3 and this is 2. So we need something that both will go into. That's 6. So I'm going to multiply the top reaction by 2 so that I get 6 electrons. And the bottom reaction by 3. And I'm going to make that a -3 because I need to also flip this equation so that the volts are positive. Right, because we're going to do this one is oxidation. So it should be flipped. So we'll rewrite that with everything distributed. Okay, notice I did not multiply the 2 by the volts or the 3 by the volts. Okay, and then add them together, or cancel out my electrons first. Add the two reactions together, and then add the volts together. I get 2.26 volts. Now if I had done this wrong, and I had flipped the top one and then added them together, I would have gotten -2.26. And a -2.26, that is not something that is spontaneous. Negative Ecells are not spontaneous. They have to be positive. All right, so remember, always flip the one that is the most negative. You keep the one that is the most positive the same, and you should be fine. All right. That's it for these notes and for the unit.